All right, in the previous notebook I showed you how we can use simulations from the Treble SDK to evaluate your neural network. Now I want to do something else. I want to actually simulate a larger training data set and use that data to train my own network. So I'm not using the previously loaded checkpoint that we used in the previous notebook, but I will actually use our own simulation data to train the network from scratch. Everybody who has done some machine learning training before knows in order to make the network generalize well to other and quite diverse conditions, we have to also have a diverse training data set that covers many degrees of freedom. Because room acoustic data sets are usually quite complex and can vary with various degrees of freedom, as seen here in this picture. For example, we can have different source-receiver configurations, as you can see here. Sources and receivers placed at different positions, but also they can have different directivities. Then we can also have different room volumes. We have small rooms, larger rooms, rooms that are somewhere in between. And we can also have different room shapes because, of course, having only shoebox rooms is very easy to do, but typical real-world rooms have more complex shapes, and that's why we also need to cover those. Additionally, we want to have different absorption properties in the rooms. We want to have very reverberant rooms, then rooms that are maybe not as reverberant, and also we want to have different placements of those absorption materials. So we want to maybe also have material properties in a way that some of the walls are very absorptive, whereas others are not and have a bit of a non-uniform absorption. And finally, what we also usually want to add into our datasets is different scattering objects, because in the real world, rooms are rarely empty. Usually, we also have some objects in there like chairs, beds, or tables. So we can see that there's quite many degrees of freedom in room acoustic datasets, and in this notebook, I want to show you that we can cover all of these with simulations from the Treble SDK. So to do this, I start by setting up a project, and I want to start with a couple of generated rooms. As you can see here, we have different shapes of rooms that we support. And in this notebook, I want to show, for example, L-shaped rooms, T-shaped rooms, U-shaped rooms. And in the Treble SDK, we have functions for all of those to automatically and randomly generate those. So you can see here all of these different A, B, C, and D parameters, for example. These are all parameters that we can randomize over to generate random rooms. And in this notebook, I will generate a total of 200 rooms. And I will show you here the functionality that we have included in the geometry definition generator, where we can create these random rooms very quickly and efficiently by randomizing over the parameter ranges as we specify here. For example, that we want to have our side A of the U-shaped room between 1.5 meters and 3 meters. So let's do this and generate 200 rooms. If you don't want to use these pre-made functions to generate rooms, you can also just specify a floor plan as a polygon and then extrude the floor plan to a certain height to get a polygon room. This could, for example, look something like this. All of the rooms that we've seen so far were pretty empty. So this is, of course, maybe a bit boring. So let's add a couple of objects into the rooms. Also there we have you covered. We have a geometry component library, and you can see here we have a couple of different groups in there, for example, tables or beds or sofas, and all of them have already a couple of objects in there. What is very important to note here is that this database is being worked on, and we will get more of those objects very soon. So let's start with one of the sofas. This looks something like this. And already here you can see, of course, this is not a sofa that I would put into my flat, but it's actually one that is optimized for room acoustic simulation. So you have nice and flat surfaces, and it's just kind of easy to use. Let's place the sofa now in our room, and we see, okay, we have our polygon room and we have the sofa in there. Maybe let's add a couple of more chairs. The chairs look like this, and we just add 3 of them. And now we see, okay, we have our polygon room, we have 3 chairs. This will not win an interior design award, but this is something that gets us started. If you don't want to place these furniture objects yourself, we can also randomly add them to the rooms. And this is what we're doing now. So in this case, we use our geometry component placement, where we can say we want to place, for example, a table or a chair or a sofa, and we want to have a certain count in each room, which is usually the maximum count, because sometimes the rooms can just be too small and we don't fit all of those in there. But then we say, okay, they can have certain angles. For example, we want to orient the tables in 90 degrees angles. And they should have a minimum distance from other objects in the room or from walls, something like that. And we will now do this and populate all of our 200 previously generated rooms with furniture. And as you can see here, this is taking a bit of time, but those are now randomly placed into the rooms. All right. Now that this is completed, we have placed random furniture in all of the 200 rooms that we previously generated. Let's have a look how this actually looks like. And we can see here we have now our U-shaped room and our objects have been placed there. So we have an armchair, we have some chairs in there, we have 2 tables where in this case, of course, as I said, we optimized them for acoustic simulations, so they don't have legs. And then we have also some boxes, for example. We can also have another look at a second one. In this case, we have a shoebox room with a very socially introvert design where you can just look at a corner and sit down on the chair here. It doesn't have to make a lot of sense, but we have added a lot of geometric detail to the rooms now that we can start to simulate. And now, if we don't want to use these rooms that we randomly generate ourselves, we can also use the database of rooms that is included in the SDK. And this database of rooms actually has in total more than 10,000 rooms in there of different categories that you can see here. So we have meeting rooms, we have classrooms, bathrooms, and so forth. And we can really choose quite nicely from these categories and from this database. And that's what I want to do in this notebook now as well. So previously we have 200 randomly generated rooms, and now I want to add 100 rooms more. So we pick 50 living rooms and 50 meeting rooms randomly from the database. And if we want to have a look, how does this room look like, we can do that. And we see, yes, this is a living room where we have a nice sofa in there and some armchair in there. And we have some table with chairs as well. And what you can see here as well is actually the suggested positions. And you can see here we have suggested positions at the dining table, for example, but also then at the armchair and the couch and so forth. And these suggested positions will be very useful for us later, because at these positions we can, for example, place sound sources or receivers. And this way we can place them at positions that are actually meaningful for that scene. What I want to do now is I want to randomly add materials to all of the layers. And once again, we see here the material library that Finner already mentioned. And we randomly place the materials at all of the 300 rooms and make sure that all of the material assignments are within a Sabine estimate of 0.4 seconds and 1 second. So now that we assigned the materials for all of those 300 rooms, we can have a look, how does it look like, and we can see we have generated a T-shaped room, and we have assigned the materials, and we also assigned the materials to the furniture that we added. Now I want to go back to this application scenario that I already mentioned in the previous notebook. So we want to do speech distance estimation. We have some speaker talking with somebody else, and this other person has a headset or AR device, for example, on it with microphones, and we want to estimate the distance between those two while we have background noise. To simulate this, we will add a couple of directional speakers in our scene, and we will add a couple of noise sources, which are omnidirectional sources, into the scene. In addition to that, we will add a couple of receivers, and that will be actually spatial receivers in this case, second order ambisonic receivers, but we could also, if we wanted to, go up to 32nd order of ambisonics. So what we are doing now is we are placing those speech sources randomly inside the scene, and what we are doing is we place them according to some rules. And those rules are that they should be at least 0.5 meters away from every surface in the room, so for example furniture, but also walls. And they should also be at least 0.5 meters away from other points that we've generated. We are using the speech directivity now and use the functionality of the SDK, which is the generate valid points. And that makes it very easy to generate those random rooms according to the rules inside all of those 300 rooms in just one for loop. Now that we included the speech sources, we will also add the noise sources into the scene. And once again, we use a point rule set there where we make sure that all of the sources that we place are at least half a meter away from all of the surfaces in the room, and also from all other points that we're generating. But then we also want to make sure that all of those noise sources are at least half a meter away from the speech sources. We generate the omnidirectional sources in there and add all of them to our rooms. And finally, we will set up grids of receivers for the generated rooms as well. So we have this functionality in the SDK that is called generate valid grid. And there we can just say that we want to have a uniform grid with a certain resolution in X, Y, and Z. And we want to also make sure that all grid points that we generate this way have, for example, a minimum distance to the surfaces in the scene or a minimum distance to the existing points in the scene. And in this case, the existing points are all of the previously generated sources, and we just make sure that all of our receivers that we generate are at least half a meter away from them. And finally, I want to show you that we can also use the position suggestions from the material database, as I mentioned before. So what I'm doing here is I will add in the database rooms, I will add my receivers at positions that are called either chair, couch, or table. And that will make the receivers be located at positions where people are usually sitting, for example, which is also nice to have a bit more informed positions for the receivers. And now that I've done all of this, I can set up my simulations and add them to the project. What I'm doing now is I'm setting up hybrid simulations with a crossover frequency at 500 Hertz. That means up to 500 Hertz we use the wave-based solvers, and above 500 Hertz we use the geometrical acoustic solver. And by doing this we make sure that we have a significant range with the wave-based solver, which gives us very highly accurate results. And now we have all those simulations added to our project, and we see in just a couple of minutes we generated quite many simulations with quite many sources and receivers in here. And if we want to kind of double check how do these look like, we can also still have a look at the simulations, and we see here this is a fairly small room, so we don't really have a big grid in there because of our rules, which were quite strict. But we have our sources in there. We have a couple of furniture objects. This is looking pretty good. We can also have a look at another example where now we have actually a significantly larger room. We see we have added a sofa in there, we have added a table in there, and we have a nice grid of receivers in addition to the sources that we have placed. And we have all the materials assigned here as well. And now we will have one final look at one of the database rooms, and we see very nicely here the receivers are actually placed at the table, so we see people are sitting at the table, whereas the sources are actually placed randomly in the room. Let's quickly estimate the runtime of this whole project, and we see here now for all of the simulations what is the estimate. And actually for simulating this entire project, which contains 20,500 room impulse responses, this would only take us something like 4.5 minutes and set us back 51 tokens. Of course, I said before, we have this knob where we can control when do the wave-based simulations start and when does the geometrical acoustic solver take over. If we were to run the same project only with geometrical acoustics, the whole estimate would look quite different. So we would be even faster. All of those simulations would run in approximately 40 seconds, and we would only have to spend 7.6 tokens on the entire dataset. Whereas if we use a 4 kilohertz crossover frequency, this would take, of course, significantly longer because we simulate a wider bandwidth with the wave-based solver, so it would take 6 hours and 20 minutes and set us back around 10,000 tokens. But once again, we have 20,500 room impulse responses in the dataset, and at 4 kilohertz crossover frequency, we also have a very large range where we use the wave-based solver and therefore get highly accurate results for our machine learning training. And what we can do now is just start all of the simulations that we have in the project, and these are 300 simulations, so let's do that. The simulations have started now, and what we can do is that we have a look at the progress now. Because what is happening is that we are now sending 300 simulations of 300 rooms and then times 5 sources, so in total 1,500 simulations. We send those to the cloud, and all of them can run in parallel. And that's what we're seeing here now, that we have quite many of those, actually 1,000 of them already in progress, whereas we have a couple more of them queued because this is my current concurrency limit. If we now let this run for a while, we would see that the simulation slowly but steadily complete. I don't want to do this now, but instead I want to use the simulations that I have already completed before the recording and use this now in the training. And once again, I want to show you now this plot where we see how does our network for the speech distance estimation work. I don't want to repeat this again, but what is important to note now is that now instead of calculating the mean absolute error as an evaluation matrix, we use this as our loss and actually feed it back to the neural network to calculate gradients and train the neural network. So essentially, to summarize, this notebook showed you how you can generate a very large and very diverse room acoustic dataset for machine learning training, and all of that used the hybrid solver that you can use from Treble, which has highly accurate simulation results.